to thank the organizers for inviting me and giving me this opportunity to talk. I'm going to talk about this geodesic metric on simple conformal loop ensemble carpets and not stable. So this is a joint work with Jason Miller. So first, let's recall what is a conformal loop symbol. So this is CLE. So first we fix a parameter kappa between 8/3 and 8, and for each simply connected domain we can define a CLE in it. So this CLE kappa in U is a random collection of non-listed non-crossing loops in U. So non-crossing means the loops do not cross themselves and also do not cross each other, but they may touch themselves and also they may touch each other, and also the domain boundary is possible. And non-listed means
the plug is very
maybe you can change the slides.
sometimes when you just like put it a bit more.
Maybe the 2000 kit.
We had this problem. I thought he even came to like change some part, but
That's true.
he's already.
they didn't.
Somebody had that issue already once, right? Like plastic.
Oh yeah, it's been happening like this maybe.
So non-listed means so no loop is surrounded by other loops. So the loops are like this, not destroyed. So they are not surrounded by any other loops. So this is a non-listed of CLE. And this is a picture of non-listed CLE3. And the white points are the points that are surrounded by some loops. So therefore the boundary of these white regions are the loops in this CLE. And it's satisfied some properties. First is the conformal invariance. So you have any cube, simply connect domain, and you choose any conformal mapping. Then the image of a CLE in this domain is a CLE in that domain. And also we have a property called restriction. So if this is U, and if you choose a smaller domain V, and you consider all the loops that are not fully containing V, so there will be something like this. And if you remove all the points that are surrounded by this loop, there will be some region left. So there will actually be infinitely many connected components of this region left. And the loops containing this region are the CLE in these things. And in different domains, in different parts, they are independent. So this is a restriction property. And once we have a non-nested CLE, we can obtain a nested CLE as follows. So first we just sample CLE, which is some loops. And in each of these loops, it is again a simply connected domain. And in each of this domain, we just sample another non-nested CLE like this. And in each of these loops, we sample again, and we do this, and so on. We do this many times, and we will obtain a nested version. And there's a phase transition for this CLE. So if kappa is between 8/3 and 4, the loops are simple and disjoint. If kappa is between 4 and 8, then the loops will touch themselves and they also touch each other and the domain boundaries. And we define a carpet or gasket. So if kappa is smaller, is at most 4, we call it a carpet, and if kappa is bigger than 4, we call it a gasket. But in both cases, it is defined to be the set of points that can connect you to boundary domain without crossing any loops. So for example, it's just this part. So for each of these points, you can find the path connected to the boundary without crossing any loops. And the reason why it is called a carpet or gasket, the name comes from the Sierpinski carpet and gasket. So this is a Sierpinski carpet is obtained by removing from a unit square some more squares. And if you consider the boundary of these removed squares as loops, these loops are destroyed. So just like the CLE cover is smaller than 4. And this Sierpinski gasket is obtained by removing from a triangle more triangles, and you can see the boundary of these triangles do touch each other and do touch the domain boundary. So just like the case we cover is bigger than 4. So this is why for the CLE carpet or gasket we call it carpet when cover is more than 4 and gasket when cover is bigger than 4. But in any cases, for all possible kappa, the Hausdorff dimension is given by this guy. And in this talk, we will focus on the case when kappa is strictly between 8 thirds and 4. So now let's recall what is the Ising model, and this Ising model gives us a motivation why it is interesting to study this CLE, and also why it is interesting to study the metric we will introduce in this talk. So let lambda be a finite subset of ZD. Let's just consider Z2 in this talk. And the Ising configuration is just assignment to each point of this lambda, either a +1 or -1. And this +1, -1 is called a thing on this point. And the Ising model is a random assignment to this point of Ising configuration. And its probability, its law is given by this formula, which depends on parameter T, which is called the temperature. And so there's a phase transition. So there's a critical temperature, also known as a Curie temperature. So below the temperature, so for all temperature below the critical temperature, as you can see, there are actually some white dots.
So did you actually simulate it?
Yeah, yes.
Yeah.
So it's not just paint and
Yes, I was always too late.
What big did that?
It's almost like one. So you can see in this case, the Ising configuration has long range order. And above the critical temperature, you can see the correlation decays exponentially. And at the critical temperature, interesting things happen, and this is what we are interested in. And so first, their theorem said that if we consider a simply connected domain U, and we intersect this with the lattice delta Z square, and we consider the Ising model on these points. And you can construct an interface. So this is, for example, if this is plus, this is minus, you just draw a path here, and if they are the same, you don't draw this. And finally, you will obtain a collection of loops in a dual graph. And the theorem says, as delta goes to 0, this collection of loops will converge to a nested CLE3 in U. And we will be interested in the scaling limit of chemical distance in these clusters. A cluster is just a connected component of plus points or minus points. And the chemical distance is just the graph distance, which is the shortest length of a path in a cluster between 2 points. And so this is a simulation of critical Ising model, and this non-white part is just one cluster, and then I randomly choose a point which is roughly there, and then I color all other points according to their distance to these points. And you can see the metric ball is quite round. It's not completely round, but similar to okay, so now we will construct a metric on this CLE carpet, which is conjectured to be the speed limit of this chemical distance on these easing models and also many other models. So let's do some results. First, I want to remark that our work is hugely inspired by some previous works on the uniqueness of liberal quantum gravity metrics, and especially these following three papers. And so instead of working on a CLE in a simply connected domain, so first we want to work on a whole plane case. So as the domain goes to infinite, goes to the whole plane, the nested CLE in a domain will converge to a thing called the whole plane nested CLE. And the reason why it is easier to work with this is that its law is invariant under translation, scaling, and also invariant. It is proved by anti-companion and Wendling. So let's introduce some notation first. So in a plane, the whole plane nested CLE, you will have like many loops and loops. And because it is scaling, in particular, there will be infinitely many loops surrounding this origin, for example. So there will be smaller and smaller points. And for each loop, for example, this is L. It corresponds to a component of the carpet, which is defined to be this part. So which is just the points surrounded by this L, but not surrounded by any loops inside. So this is the components corresponding to L. And now we want to consider simultaneously all the components. So I just take a disjoint union for all these components. So this guy is called, I call it epsilon L, and I just take a disjoint union. So one thing you need to be careful is that for each point on the loop, it actually corresponds to 2 points in this disjoint union. 1 point corresponds to the component in this component, and another point corresponds to this component. So this need to be careful.
Is this whole plane nested CLE still a probability measure?
Yes. Yes, it is because it is nested. Okay, there are some notation for metric. So a metric space is called a geodesic metric if for any 2 points there is a geodesic connecting these 2 points, and a geodesic is just a path whose length is just a distance between these 2 points. And also this is a metric space X, and for subset Y, we can define an induced intrinsic metric in Y, which is for any 2 points between Y. We consider all the paths in Y connecting these 2 points, and which we consider the infimum over all these paths connecting these 2 points, but contained inside Y. And so this is defined to be induced intrinsic metric. And a metric is a length metric if it is an induced metric of itself, which means for any 2 points x, y, and for any epsilon, there will be a path connecting x and y whose length is at most dxy plus epsilon. So a geodesic metric is always a length metric, but not on the other way. So now we give some axioms that we think every natural CLE, natural metric on the CLE carpet should satisfy. And later we will prove there exists a unique one satisfy these axioms. So it is a measurable mapping from this CLE open configuration to a metric called D epsilon, such as the following conditions, etc. First, it is a geodesic metric, which means there's another notation. So here we write this x left, right arrow y if they are in the same component. It just means they are in the same epsilon L for some L. And because we don't want the geodesic to cross any loops, so we can only consider distance between any 2 points in the same component of this epsilon. And we just let the distance between any other points that are not in the same component to be infinity. So this D is a geodesic metric, and it is finite if and only they're in the same component. And the locality says that, so this is our configuration, and if we just choose any open set U in a plane, the induced metric inside is almost surely determined by the configuration inside. And also there's a translation and scaling covariance, which says that if we just translate the configuration, the distance between 2 points stays the same. And if we multiply the configuration by r, then the distance between 2 points get multiplied by r to the power of some theta. Theta is a deterministic constant, and we'll call it a distance exponent.
So why don't you require inversion invariance? So
we don't need to use inversion to prove uniqueness.
okay.
But I think it is satisfied once we construct this thing. And also we don't require the rotation invariance here, but you can also prove it is satisfied once you have
So
this.
it's more like covariance, right? Inversion like conformal.
Yeah,
Conformal covariance.
That was my understanding.
And finally, there's a tightness, which roughly says that the metric is order continuous with respect to the Euclidean metric on each component. And in particular, because this metric is continuous with respect to the Euclidean metric, and each component, this epsilon L, is compact in Euclidean topology. So this will implies that this metric also induces Euclidean topology on each.
You need the strong tightness thing for the. You need to assume that, or is it?
Yeah, yes, we
The
actually.
others are not enough.
Yeah, actually, well, in our proof, we actually need to assume.
So the theta is something like 2 minus the dimension of the perfect, or
This kite.
the theta is the dimension of the dimension of the carpet, right?
This theta.
Yeah, the theta.
Theta is not the dimension of, but it's related. I will talk about this later. Yeah, theta is related to several dimensions. So first we prove the existence. So we find some approximations. Approximation is given for any 2 points x and y.
By the way, sorry to go again, like at the locality thing. This should be, so the function that gives the locality should also be translation invariant. So if we translate u,
Yes, but we don't assume it.
We don't assume.
Yeah, we don't assume it.
Okay.
Yeah, it should be true, but we don't assume it. Yeah.
Okay.
But we have translation invariance. So the third axiom, I think it plays the role of what you are saying.
Right. Yeah. Okay. Right. I see.
So we define approximation for any 2 points x, y that are in the same component. We just consider all paths in this epsilon L connect these 2 points. This is P, for example, and we consider a epsilon neighborhood of these paths, and we consider the weight measure of this epsilon neighborhood, and we choose the infimum. And this is d epsilon xy. And of course, as epsilon goes to 0, this guy will also go to 0. So we need some normalization. So what we can prove is that there exists a family of normalization constants such that for every sequence of epsilon goes to 0, there exists a subsequence such that these approximations converge to some CLE carpet metric. So in particular, this shows the existence of our CLE carpet metric. The uniqueness, there will be 2 parts of the uniqueness. First, we say that we just assume that there are 2 carpet metrics, but they have the same distance exponent. Then we can prove that they are the same up to a multiplicative constant. And the second part, we prove that there is a unique theta for which a CLE carpet metric with this exponent exists. So in total, there will be only 1. And so now I want to discuss this distance exponent because it is also a very important constant that are studied a lot in physics. So first, in this talk, we only consider 8/3 between 8/3 and 4, but there's also a version between 4 and 8. I will also mention this later. And for both these cases, we have the estimates. This is proved by Liam Hughes in his thesis.
I have not seen that paper anywhere yet. Is it?
It's in his thesis you can find in some Cambridge website.
So he hasn't put a paper on.
No, I don't think so.
And that 4 is not included in any of the.
4 is not included.
Okay.
I will also mention why.
Yeah, because I was claiming this thing in my talk always, but like I thought that this was some ongoing project that they never finished or something like that.
Yeah, but yeah.
Yeah, I thought that like because I think they wanted to show something else, right? They wanted to show that the geodesics are not SLE and that they got stuck at some point, you know? And then they never finished that.
But maybe you could extract that part.
Yeah.
So this distance exponent is obtained from continuum setting. So we construct a metric on CLE, which is a continuum thing, and we obtain this exponent. And there's also we can also study this exponent from the discrete setting. For example, in the population setting, which corresponds to kappa equal to 6, it is first conjectured by Kirsten Zhang that this theta is strictly smaller than 4/3, and later proved by Dharma, Hansen, and Sosoi. And you can also observe that this 4/3 is exactly this when kappa is 6. So these 2 artibounds matches. And there's also some, for the Ising model, which correspond to kappa equal to 3, there are some simulations recently which says that it's roughly this guy, and yeah, it is.
What is the geometrical meaning of this exponent one plus 2 over gamma?
Sorry?
So you get this kind of bound, but is there some meaning of this bound?
I think this, I'm not sure about non-simple case, but when kappa is smaller than 4, this bound is quite trivial because it's just because this 1 plus kappa over 8 is just the dimension of SLE curve. So it's a dimension of this.
Yeah, I understand this bound, but what the kappa larger than 4 is.
You can put 16 over kappa and get that one, but it's not geometric meaning.
It's the outer boundary. You can always, if you don't enter, so that the non-simple ones have some parts that are disconnected by one point. If you don't cross those points, then that's what you get.
Okay, I see.
And then we want to conjecture that this theta is strictly increasing in kappa and it's continuous. And also, as kappa goes to 8 thirds, from the right, this theta goes to 1. This is because as kappa goes to 8 thirds, the CLE kappa goes to nothing, it's just an empty set. So when the CLE is empty, the carpet is just the domain. And in this case, the CLE carpet metric is just the Euclidean metric. So we conjecture it goes to 1. But we don't know how to prove this at this moment. And also we have some results about the Hausdorff dimension. So first we know that Hausdorff dimension of the carpet is given by this formula. And now we can prove that the dimension of the carpet with respect to this carpet metric is given by this dimension divided by theta. And we can also prove that almost surely every geodesic, the Hausdorff dimension with respect to the Euclidean metric is equal to theta. And now actually we want to conjecture that up to a multiplicative constant, that the length of each geodesic is actually given by the theta dimensional Minkowski content of this geodesic. So this is quite interesting because from an axiom before, from this locality, we already know that the length of a geodesic is determined by any open neighborhood of this geodesic. The length of this is determined by open neighborhood. But if this conjecture is true, this conjecture is true, then the length of the geodesic is actually just determined by the path itself. And another result we have is this conference of geodesics. So now we consider the geodesics, so we can just try to focus on one exponent, one component of the carpet. So for example, we can just choose this one. So this is unit is. And there is a largest loop containing this unit is that also surrounds this origin. And there are some more loops. And now we just consider these components. And there's a very natural measure on this carpet constructed by Jason and Lucas. And so if you sample points using this measure, you can just view these points as focal points in this carpet. So now let's sample several points independently from this measure. And we conjecture that for any two typical points, there exists a unique geodesic connecting x and y. There's a unique geodesic. But be careful that this just means if you sample 2 points, there is almost surely one geodesic. But almost surely there should be 2 points that have more than one geodesic. So there's a difference between the order of where you put this almost surely. And another very interesting result is a confluence. Is that if you choose 3 points, x, y, and z, and if you consider the geodesic from x to z and from y to z, actually this theorem should be only true for not the geodesics from x to z, but the leftmost. Because now, if we don't know this conjecture, we can only prove this theorem for the leftmost geodesics. So there's a table here. If we consider leftmost geodesics from x to z and also y to z, we can show that they must merge before hitting z, before reaching z. So there's another table. This reaching x will be reaching z. And you can see in this simulation. So this is the center points I choose, and I then randomly sample like 100 other points, and I draw the geodesic from these points to these other points. So these are the geodesics, and you can see they do merge before reaching the origin. And once we have defined a CLE carpet metric for the carpet of a whole plane nested one, we can also use it to define a metric for any general domains. So the definition is like this. You just choose a U, and you fix a point Z inside, and you also consider the whole plane nested CLE, and there will be a largest loop that is containing U and surrounds Z. And you condition on the event that this loop is close to the boundary. And you take a limit that condition on this loop like converge to the boundary of U. Then a metric on this carpet will converge to a metric on the carpet of a non-nested CLE in U. But be careful, we will, so as we take limit, this will converge to a metric in the carpet of a non-nested CLE in U. But the one thing we need to be careful is that this metric, first, it is a length metric, and second, it is only defined on the carpet minus the domain boundary. So the reason is that if the boundary of U is too smooth, for example, if this arc of the boundary is too smooth, then the distance between these 2 points will be 0. And if some part of the domain boundary is too rough, then it is possible that some points on the boundary has infinite distance to any other points. So only in the case that the domain boundary looks like a SLE loop, something like an SLE loop, we can define the metric also on the boundary. So for general domain, we only have carpet minus the domain boundary. And
But then the geodesic will go along the boundary, right?
yes, that's why we only call it a length metric, because
Okay, I see.
yes. Yeah. So if this arc is too smooth,
Yeah.
then the geodesic between these 2 points, it is possible it will.
Yeah, it will go.
Yeah.
I see.
So we only your length metric. And once we define it for any domains, we have a conformal covariance. It is stronger than our translation and scaling covariance before. It is valid for any conformal mapping. So if we have a lower metric on U, we map this U to any other domain phi U, and we also map the CLE to here. Then the metric on this carpet can be obtained from the metric on this carpet by this formula. And also there's a locality. So this locality is also stronger than the one before. For example, now you choose a subdomain V, and you remove all these loops, and also there are loops here, and also there are loops here. And then the things inside is also a CLE in this part. So we can know that the induced metric inside here is not only almost surely determined by things inside, which we said before. It is actually given by the CLE in this domain. So these are all the results, and I want to mention some related works and future questions. So firstly, there's a version for cover prime between 4 and 8. It's done by Yijen, which is here, and Jason and Valeria. And so by a similar argument, we can also construct your quantum gravity metric on these CLE carpets. And in some part of the proof, the proof is actually much simpler. So I skip the detail of this metric. So this is this is something for you, and you have a non-nested CLE in U, and you also have a Gaussian free field on this domain U, and this Gaussian free field and this CLE are independent, and then you can define your quantum gravity metric on this target. By a similar argument. So this object is also interesting because it's related to some other things. So that alpha is given by this formula, and so it's related to a thing called stable carpet. We have already.
In that, what is the relationship there then between the CLE carpet metric and the gamma LQG metric? Or why is it so much easier?
I don't think there's direct relation between these two. Or maybe there's some KPZ formula, I guess. I'm not sure. But so the proof of this CLE metric, we also use average surface, and we first prove something for the average surface, and when we transfer it back to the CLE. So this is like the CLE metric with respect to Euclidean metric, like this, and this is like CLE metric with respect to the LPG.
Okay.
And maybe let me just state. So there's a sphere version and the disk version of this conjecture. Let me just say the disk version is simpler. So first we sample a gamma numerical gravity disk, and then we sample an independent CLE on this disk. And then there will be a natural quantum gravity measure on this carpet, which is constructed in a paper by Jason Scott and Wembley. And if we condition on the event that this LVG measure on this carpet is equal to 1, then this metric measure space, so this carpet equipped with a metric, it also equipped with this measure, is a disk variant of something called the alpha stable carpet. This is constructed in the paper by Ivan Korean, and Rivera.
What
So
is the version of the stable carpet? Do they have something like that, or is this something?
Yeah, they constructed something called this stable.
Yeah, but they don't have the disk thing, right? Or does it follow somehow?
They proved it for the sphere version, I think.
Yeah.
I think there will be a disk version.
What do you mean here by, so the alpha stable carpet is a triplet of the gasket, the distance, and I guess a measure, and then what do you mean, so the disk variant is, you just then consider the epsilon on the disk ends on the disk, or the measure on the
In the
LQG disk basically, so you take then
in their paper, actually, they construct something in the topology in the sphere. So you can also, if you consider the sphere case, you can also do things like this. So for example, if you first sample a gamma LVG sphere, and this is infinity, and there's also a point called 0 and infinity. And then you can actually sample a CLE on this sphere, but conditioned that the 0 and infinity are contained in a carpet. This is a 0 probability event, but it is proved by Scott Sheffield, Samuel Watson, and Howell that we can condition on this event. So there will be some loops on this sphere. No loops around this 0 and infinity. And then you
Is there a reason you want to condition on that? What's the reason you want to condition on 0 and infinity in the carpet?
otherwise you won't get a probability measure.
I mean, okay, but like if you don't condition, you can select any. I'm just a bit wondering because the stable gasket doesn't have such a condition in there, right? So I mean,
Which condition?
this conditioning on two special points.
I mean, if you want to define a non-nested CLE on a sphere, you need to condition on something. Otherwise, it's not a probability measure. It's like if you have considered whole plane non-nested CLE,
Yeah,
it's not a probability measure.
Okay. But that's the only reason, yeah. So there's no. Okay.
Yeah, yes.
So, but you could like I don't know, say you take the outermost cluster that surrounds the disk or something like that, and then like select a cluster in some way. That should.
And also in their construction of stable carpet, there are also two typical points. They are also equipped with two typical points in the carpet.
Do you have these points? Okay. But in that case, their 2 points are somehow resampling invariant, right? If I remember correctly.
Oh yes. So yeah, I said here a variant of. So because for the LBG sphere, these 2 points are typical points for the LBG measure on the sphere. But here we want these 2 points to be typical points for the LBG measure on the carpet.
Right.
So there's a difference. So yeah, you have to take a variant.
Okay.
Yeah, something like that, but these two objects should be.
I should remember because I gave this as an essay, but I forgot already.
Yeah, another thing that is related and very interesting is the running motion of this CLE carpet or gasket. So let's first recall some history. The running motion of Sierpinski gasket and carpet. So in 1988, Martin Barlow and Perkins constructed a running motion on the Sierpinski gasket, and they also proved the uniqueness of their running motion, and that satisfies several like self-similarity axioms. And then later in 1989 and 1992, there are also two constructions of the running motion on this Sierpinski carpet. But what they actually do is prove some tightness or some approximations of this running motion in this carpet. But what they do not know is the uniqueness of their subsequential limit, and they also do not know whether these two constructions will give the same object. Not until 20 years later in 2010, proved by all of us, Margaya and Tebiev, that the uniqueness is true. So this says that the construction of running motion of Sierpinski carpet is much more difficult than the gasket. So the reason is because the non-existence of card points. So the card points are like these points that these triangles intersect, like these, and also these. So these card points are special because if you have a Brownian motion that starts with somewhere here, you want to go to somewhere here, then it has to pass through these points. So knowing this fact is like super useful for studying these Brownian motions. So you can also get similar difficulty arise for the CLE. So and why this Brownian motion is related to the things we talked today is because there's a framework introduced by Jun Kitami called resistance form and resistance matrix in order to construct Brownian motions on fractal sets. And the philosophy is that it usually works when the dimension is strictly less than 2. So roughly speaking, a resistance form on a set X is a pair E and F. F is a linear subspace of the space of all functions from X to R and containing the constant functions. And E is a non-negative definite symmetric binomial form on F that satisfy a bunch of conditions that I speak in this talk. And once you have a resistant form, you can define a metric by this formula. So this gives you a metric, and it is called the resistance metric associated with this. And if you assume in this metric the space is separable and compact, then the form is uniquely determined by R, which says more or less these two things are equivalent. So once you have one, you can have another one. And why this thing is helpful to study Brownian motion is because this resistance form will generate a Hill kernel. And if it satisfies another property called the locality property, because you have a Hill kernel, you can define a macro process by requiring the transition density to be this Hill kernel. You will get a macro process, and if this form satisfies another property called locality, then in the macro process, your plane will actually be continuous. The continuous macro process. We call it diffusion. And usually, if you get a diffusion on a fractal set, we call it a Brownian motion on this fractal set. Yes. And recently, there's some work by Jason and some other students. They constructed a canonical resistance metric on the CLE kappa prime cascade. So the kappa prime is between 4 and 8. And they also proved that when kappa prime is 6, it is indeed the scaling limit of resistance metric on the clusters of critical population model. Because for any graph, you can also define resistance metric. So for this cluster, you can define resistance metric. And they prove it is indeed the scaling limit. And there was a result by David Croydon, says that if you have a convergence of resistance metric, then the associated process also converge. So combining this result and this result, we obtain that the random walk on the critical population cluster indeed converge to the Brownian motion in the CLE kappa prime cascade they constructed. So they constructed a resistance metric, and this by the framework we talked just before, it gives rise to a Brownian motion on a cascade, and this implies the simple random walk on critical population cluster converge to the Brownian motion. And there was another work by Kirsten, and also this paper says that this Brownian motion when kappa prime is 6, it is a subdiffusion. So it should be a subdiffusion for all kappa, but I guess we do not know. Do you know this? For other
What?
I think the Brownian motion for kappa prime should be a subdiffusion.
It's subdiffusive. Good question. I don't think we have shown this, but it should be. Yeah.
So it should be true for all kappa prime, but now
Yeah, it should be.
we have some result from Kirsten. We know that it is true for kappa prime equal to 6 now. So Jason and me are now working, trying to construct this also for CLE carpet, and hopefully this question mark will be at most 6, maybe.
Do you have to do this like a tightness proof? Do you need to do something completely different for the geodesic case, or do you?
So we guess that the techniques that are used to construct the geodesic metric should be somehow also useful to construct this resistance metric. But of course they are not the same thing, so there will be more difficulties.
Yeah. But you expect the same strategy should somehow work, right?
Yeah, some of the main idea should be the same. So now I sketch some proof of uniqueness. So there will be. So let's go back to the setting of a whole plane density, CLE, and first there's a two technique lemma that is very useful. So one is the independence across scale, which roughly says if you consider a sequence of disjoint, concentric annuli, and you have event ei plus 1, things like this, and you require the event depend only on configurations inside these annulus. And if you know that each event has probability big enough, then this lemma roughly says that we will have a lot of annuli for which the corresponding event actually happens. So for example, you can imagine if the configuration inside these annuli are actually independent, then this should be true. But since they are not independent, but we have some near independence. So this is already proved by Valeria, Jason, and Ingen for the non-simple case, but a similar argument can also work for the simple case. And another estimate that is very useful is the estimate for forearms. The forearm is that if you consider annulus and a CLE, there will be almost surely only finitely many these arcs of CLE loops that crosses between the inner and outer boundaries. And if this look like this, we call it the forearm events. And the probability of this forearm events, the ratio of this thing is like epsilon to 1. Then this forearm events is up to a constant bounded by epsilon to some alpha. Alpha is a constant that is bigger than 2. This is very useful because it is important that alpha is bigger than 2. Because if it is bigger than 2, then you can just take a union bound, you can cover the whole region using this by this annulus. You can find many annulus such that this inner ball covers the whole region. So you can find many annulus such that their inner ball covers the whole region, and this event don't occur for each of them. And why this event is important is that if we have at most 2 arms, so for example, if this is a loop and there are no other arms, then we can always find a path. This path is in the carpet. So this path in the carpet, this is a loop. And if we have this path, then every other geodesic, this is a geodesic, that enters this inner ball must cross this path. So in particular, if this is a geodesic, then by definition, the geodesic, the distance between these 2 points is at most the length of this thing around. So this is a very useful technique here. And now, the major part of this paper is to prove uniqueness. So for 2 metric with the same distance exponent, they are the same up to a constant. So first, it follows almost immediately from the above 2 techniques that they are bi-Lifshitz equivalence, and then we can define this optimal bi-Lifshitz constant. So then by step 1, this is strictly between 0 and infinity, and we have this is true almost surely. And our goal is to prove these 2 optimal bi-Lifshitz coefficients are actually the same. So we suppose that they are not the same, then there are many shortcuts. Shortcuts are points that pairs of points x, y, such that the ratio of d tilde over d of their distance is bounded away from the upper optimal by Lipschitz coefficient. So we can prove that there are a lot of shortcuts. There are shortcuts everywhere. And if there are shortcuts everywhere, then we can prove by some resampling argument that every geodesic must get close to many shortcuts. The argument is like this. So there are some good balls satisfy some events, and these are just two sets. And this red path is a geodesic before resampling. So they enter these balls. And then we perform some resampling inside this ball. And after resampling, we will obtain this. So these blue arcs are CLE loops. So this is a CLE loop. And this arc is part of a CLE loop. So the rest of it is not important. I didn't draw it. But these CLE loops that form a tube. And it forms a tube, and if you want to go through this ball, you have to enter this tube. And we also require so these brown things are shortcuts. So therefore, if this light blue ones denotes the new geodesic after resampling, the new geodesic must goes close to many of these shortcuts. So by this resampling argument, we can show that every geodesic gets close to many shortcuts. And because a shortcut is 2 points that their ratio is bounded away from the optimal constant. And if a geodesic goes close to many shortcuts, their ratio must be also bounded away from the optimal constant. But this contradicts the optimality. And finally, I want to just remark. So the main ideas of this proof of these steps is similar to the proof of Euro quantum gravity metric, but because for Gaussian free field we can always add a function and minus a function, and you have a nice mark of working for GFF. So it adds many changes in this case. Thank you.